Okay, for section 11.8b, let's look at another example. So the problem says the sum from n equals 0 to infinity. We have negative 3 to the n, x to the n, over the square root of n plus 1. Now, we use the ratio test many times, so we often use the ratio test when we're determining our radius of convergence. Sometimes we will use the root test, but they always fail when x is an endpoint. So you have to check your endpoints with other things, like in the other video when we used 2 and 4 in that one example. So on this problem, we're supposed to find the radius of convergence and the interval of convergence. So let's look at the ratio test because we have powers here, and the root test isn't going to be helpful. So let's look at the ratio test. We have the limit as n approaches infinity. So our numerator is negative 3 to the n plus 1, x to the n plus 1, over the square root of n plus 1, divided by, sorry, I forgot I was doing another fraction in there, divided by negative 3 to the n, x to the n, over the square root of n plus 1. So let's say the limit as n approaches infinity. We have negative 3 to the n plus 1, negative 3 to the n times negative 3, x to the n, x to the 1, over the square root of n plus 2, times the square root of n plus 1 is on top. We have negative 3 to the n, x to the n. So let's look at the fact that these x to the n's cancel, the negative 3 to the n's cancel. So we now have the limit as n approaches infinity. Now in the numerator we have negative 3, but the absolute value of negative 3 is 3. So we don't need to write the negative. And we have an x, and we have the square root of n plus 1 over the denominator is the square root of n plus 2. You could use L'Hopital's rule here, but I think it's messier. By the way, you evaluate and you get infinity over infinity in determinate form. Sorry, jumped the gun. You could use L'Hopital's rule, but it's messier. So let's keep this and let's divide by the highest power of n in the denominator. So we're going to divide by the square root of n. Now when you look at this in the limits, this right here approaches 0, and this approaches 0 as well. So then we have the limit as n approaches infinity of the absolute value of 3x over, and we have the square root of 1 over the square root of 1, which equals the absolute value of 3x. Now, since we're in the ratio test, if the absolute value of 3x is less than 1, then we have convergent. And if the absolute value of 3x is greater than 1, then we have divergent. So let's solve the absolute value of 3x is less than 1. So that means negative 1 is less than 3x, which is less than 1. So negative 1/3 is less than x, which is less than 1/3. So we know it's convergent in this space. That means it's divergent when x is less than negative 1/3 or x is greater than positive 1/3. That's divergent. So now we need to look at the endpoints. The endpoints are x equals negative 1/3 and x equals positive 1/3. So let's start with x equals negative 1/3. So we say the series says negative 3 to the n x to the n over the square root of n plus 1, n equals 0 to infinity. So when we test for our endpoints, we're putting those in for x. So we say the series from n equals 0 to infinity, negative 3 to the n, negative 1/3 to the n, over the square root of n plus 1. Well, that means that we have the square root, or the series from n equals 0 to infinity. And these two here multiply. They both have an n power. So we could say negative 3 times negative 1/3 all to the n power over the square root of n plus 1, which is the series from n equals 0 to infinity. We have positive 1 to the n, which is 1, over the square root of n plus 1. Now this is 1 over 1 plus 1 over the square root of 2 plus 1 over the square root of 3 plus, now there's several things we can use here. I see positive decreasing continuous. So let's consider the integral from 1 to infinity of 1 over the square root of n plus 1, x. 1 over the square root of x plus 1 dx. So this is the limit as m approaches infinity. The integral from 1 to m, 1 over the square root of x plus 1 dx. So we let u equal x plus 1 and du equals dx. So we have the limit as m approaches infinity. The integral from 1 to m, 1 over the square root of u du, which is the limit as m approaches infinity. The integral from 1 to m, u to the minus 1/2 du. So we integrate and we get, we add 1 to be u to the 1/2, flip and multiply to be 2 from 1 to m. So we have the limit as m approaches infinity, 2 times the square root of x plus 1 from 1 to m. So we have the limit as m approaches infinity. We have 2 times the square root of m plus 1 minus 2 times the square root of 2. And this goes to infinity, and infinity minus that is infinity, which is divergent. So since the improper integral is divergent, that means that the series when x equals negative 1/3 diverges. It's divergent as well. So now we need to look at x equals positive 1/3. So we have the same series from n equals 0 to infinity, negative 3 to the n, positive 1/3 to the n, over the square root of n plus 1. So this becomes the series from n equals 0 to infinity. And we have negative 3 times 1/3 is negative 1 to the n over the square root of n plus 1. So if we put in 0, we have 1. If we put in 1, we have negative 1 over the square root of 2. 2 would give us positive 1 over the square root of 3. So we have an alternating series here. Well, we tend to write plus ... And I didn't want to do any more, so we'll do that. So let's look at the alternating series. First of all, b sub n plus 1 is less than or equal to b sub n. That is a true statement. We are descending here. So condition 1 is satisfied. Let's check condition 2. The limit as n approaches infinity of 1 over the square root of n plus 1 becomes 1 over infinity, which is 0. Therefore, this series, this alternating series, is convergent. So that means x equals 1/3, positive 1/3 is convergent. Now let's go back to the work that we had before. And we were asked to find, let's go back to the top. We were asked to find the radius of convergence and the interval of convergence. So this right here gives us our radius of convergence. So when we get to this point, we can say that r equals 1/3. Now we can get there using this equation. Let's put it in blue as well. Or we can do it here, and from here we could say that the absolute value of x equals 1/3. So then r equals 1/3. So no matter if you want to come from your inequality or if you want to come from there, your radius is, the radius of convergence is 1/3. And then we had that interval, negative 1/3 to positive 1/3, but we had to check our endpoints. And we found that negative 1/3 was divergent. That x, let's add to it, x equals negative 1/3 is divergent. And x equals positive 1/3 is convergent. So that means our interval would be including the positive 1/3. So we're going to write this nicely over here. And let's say r equals 1/3 is the radius of convergence. And the interval is negative 1/3 to positive 1/3. So that handles it all. I think that's all you need there. So let's look at another one. It says find the radius of convergence. Radius of convergence. And the interval of convergence. And the problem says the series from n equals 0 to infinity, n times x plus 2 to the n over 3 to the n plus 1. So let's look at our ratio test again. The ratio test is very handy. So we say the limit is n approaches infinity, big fraction, n plus 1, x plus 2 to the n plus 1, over 3 to the n plus 1 plus 1. And in the denominator we have n times x plus 2 to the n over 3 to the n plus 1. There are people who kind of like to work through this step in a different way. I think it's easier to see every part of it. So we have x plus 2 to the n, x plus 2, because that makes n plus 1. When you multiply bases, you add exponents. And here I have n, x plus 2 to the n. And then from the denominator, we have 3 to the n plus 1, which is 3 to the n times 3. We'll leave it like that. And then on the bottom, we have 3 to the n plus 1 times 3, because that's our plus 1. End absolute value signs. Now you can see these 3 to the n plus 1s cancel. The x plus 2 to the n's cancel. So now we have the limit as n approaches infinity. The numerator has an x plus 2 and an n plus 1. And the denominator has a 3 and an n. So if we plug in infinity, we get infinity times x plus 2 over infinity times 3 in determinate form. I love L'Hopital's rule, and it works here. So let's look at L'Hopital's rule. So we have the limit as n approaches infinity. Now x plus 2 is a constant, so let's go ahead and bring that down. And the derivative of n plus 1 is 1, and the derivative of 3n is 3. So we end up with the absolute value of x plus 2 over 3. So let's look at we know that by the ratio test, if this is less than 1, then we have convergent. So let's solve it for the absolute value. So that means that the absolute value of x plus 2 is less than 3. Now, if you notice, this x plus 2 is the power that we have back here in the problem. See the x plus 2? So the fact that the x plus 2 is less than 3, this means our radius of convergence is r equals 3. So to find the interval, we now need to solve that. So let's say x plus 2 is less than 3 and is greater than negative 3. We have to solve for x so we can check our endpoints. We're going to subtract 2 in every area, just a reminder in case you forgot. Negative 5 is less than x, which is less than 1. So that's our interval for convergence, but we have to check the endpoints. So we're going to start with, let's start with the lower one. Let's say x equals negative 5. So this means we have the series from n equals 0 to infinity, n times negative 5 plus 2 to the n power over 3 to the n plus 1. So that gives us the series from n equals 0 to infinity, n times negative 3 to the n over 3 to the n plus 1. So now let's write this as the series from n equals 0 to infinity. Let's pull out the negative 1 to the n, and then multiply it by 3n over 3 to the n plus 1. Because I left off a power. Let's go back. This would be times 3 to the n, because that gives us this negative 3 to the n, and then we have an n here. Now, as you can see before, this 3 on the bottom, this 3 to the n plus 1. So we have negative 1 to the n times 3 to the n times n. And on the bottom, we have 3 to the n times 3. So now we have the series n equals 0 to infinity. Negative 1 to the n times n over 3. Well, that's just a constant. So we have the sum n equals 0 to infinity, negative 1 to the n power over 3 times n. Do you see the n happening right there? We can use our summation laws and bring out the 1/3. So we have negative 1 to the nth power times n. That is not decreasing, and so it fails the alternating series test. So we look at the test for divergence. Let's do it under here, test for divergence. It says that we take the limit as n approaches infinity of the summation. So we have the series negative 1 to the n, which is divergent. It does not exist. Does not equal 0, so it is divergent. So when x equals negative 5, we have divergent. So we need to check the other endpoint. Let's do it in this space here. The other endpoint is x equals 1. You got the divergence down there. Okay, so now let's look at x equals 1. So we have the sum from n equals 0 to infinity. And the problem was n times x, which is 1 plus 2 to the n over 3 to the n plus 1. So we have the sum from n equals 0 to infinity, n times 3 to the n over 3 to the n plus 1. Well, by now we should know this is n equals 0 to the infinity. So we have 1 over 3 times n. So if you look at that, that is not decreasing. So let's look at the test for divergence here. This one's even easier. So we say the limit as n approaches infinity of 1/3 n, which equals 1/3 times infinity, which is infinity, so we have divergent. So both of our endpoints are divergent. So when we come back up here, this is our convergent, and we found both endpoints down here to be divergent. So that means we can say that the -5 to 1 is the interval of convergence. So that's our answer right here. We have the interval of convergence and we have the radius of convergence, so the problem is done. So I think you've got everything you need to wrap up this section, and let me know if you have any questions. Thank you.